All right. What we learned about in this chapter, this kinetics chapter, was talking about how fast reactions go, the rate of a reaction, right? And so what we learned how to do is take some data here, this initial rate data, and given this rate law expression here, we can find the order of this reaction, find these two exponents here. And so that's what we did last class, was analyze this data in order to figure out this rate expression, right? And in particular, it was this second order portion right here that we didn't know that we had to get from our data. And once we determine the order of the reaction, we could even go a step further in terms of determining the K of this reaction, the rate constant, right? So now we have built our rate expression from this data here. That is a big portion of what we learned how to do this chapter. Analyze this initial rate data in order to get our full rate expression. And since it's a second order reaction, we can then pick the appropriate integrated rate law, which would in this case be this one. We can plug in our data for the initial concentration of A. That's what these terms are here. And that value of K that we solved for. And this will allow us to predict what happens to the concentration of A at each point in the future, right? What's happening to our reactant concentration as this reaction is going down. All right. And so using that rate expression there, you can plug in different values of T. So for this, I chose that first data point where that initial concentration of A is 0.1 and use that value of K that we found of 0.21, plug that into my integrated rate law here. So at T equals 0, it's just that initial concentration of A. And then I can figure out what happens to the concentration of A at each point in the future. All right, and so then what I did was I just put this into an Excel spreadsheet at a bunch of different time points, and I get what happens to the concentration of A over time, and I get this little curve here where I see my reactant being consumed. Okay, so that's what we can do with our integrated rate law, is use it to predict what's going to happen to the concentration of reactant at any point in the future, right? Once we know the order of our reaction, we know which one of our integrated rate laws to choose, and we can figure out how the concentration of A will change over time. What I did here was I then, for comparison, I then used the integrated rate law for a first order reaction. I used that same initial value of A and that same value of K and calculated the concentration of A as it changes over time. And what you can see is that even though the concentration of A initially and that value for K is the same, I get a different curve here for my first order reaction, where the concentration of A decreases much faster, right? And this is just a signature of these two types of reactions. The rate of a second order reaction depends much more on the concentration of A. So it's much more sensitive to the concentration of A. So as that reactant starts to get consumed, these second order reactions slow down much faster compared to a first order reaction. And this is even more than if I were to plot a 0th order reaction, that would be even quicker. It would look something like this as a just straight line. And that is even faster, given that same initial concentration and same value for K. All right, so that's what I can do with my integrated rate laws. These aren't things that you have to have memorized or things that you need to be able to do the calculus to derive yourself. They are on our formulas page. They're on our constants page. You just need to know when it's appropriate to use it, right? So you need to first figure out the order of your reaction. That will then tell you which one of your integrated rate laws you can use. Okay. The other thing we're going to learn, which is kind of similar, not something that you have to have memorized, but something that you need to know how to use, is what's called the half-life of a reaction. Okay, so this is the time that it takes for half of your initial concentration of A to be consumed. And for a 0 order reaction, so this is for a 0 order reaction, our half-life expression is the concentration of A initially divided by 2K. Right, so again, once you've gone through and figured out the order of a reaction, and have found that value for K, both things we can do with our initial rate data, you can figure out not only how the concentration of A will change over time, but also the half-life of that reaction. All right, how much time does it take for half of your initial concentration to be consumed? For a first order reaction, we can also define the half-life. And this is going to be equal to the negative natural log of 1/2 divided by K. All right, so interestingly, for a first order reaction, the half-life is independent of the initial concentration of A. Notice how that doesn't appear anywhere in this term. So it turns out that for a first order reaction, it doesn't matter how much you start out with. The half-life of that reaction, the time it takes to consume half of your reactant, is independent of how much you start with. All right, it is dependent on your rate constant K, but not on that initial concentration. And then lastly, for a second order reaction, we can again define our half-life. And that is going to be equal to 1/K times the concentration of A. All right, and for a second order reaction, you can see that it's actually inversely proportional to the concentration of A, which means that the more reactant that you start out with, the longer it's going to take your reaction, right? The longer it's going to take to reach that half-life for a second order reaction, because again, second order reactions are very sensitive to the concentration of your reactant. Okay, so again, once I've taken my initial rate data, I've analyzed it like we showed how to do last class to figure out the order of my reaction. So that's what I've solved here, as well as the value of that rate constant. Now I know where to, which integrated rate law to choose. So that was a second order. So I would choose this one here. And I could either use this function to predict how the concentration of A will change over time, or this half-life value in order to figure out how long it's going to take for half of my concentration of A to be used up, right? For the concentration of A to be cut in half. Okay, cool. So that is stuff that we can do from that initial rate data here. All right. So now we're going to go back and talk about something that we discussed at the very beginning of this whole thing. Right, we're going to make this plot real quick. Where on this axis we have energy, and on this axis we have reaction, progress. Sometimes it's called reaction coordinates. Okay, and this is this reaction progress diagram here. And there are these curves that look, kind of like flat here, then they go up, come back down before leveling off. And we took a look at this curve when we discussed thermodynamics, and we said that the only portion of this curve that corresponds to the thermodynamics of a reaction is the initial energy of your reactants. So over here, I have my reactant energy. Over here, I have my product energy. So this level here and this level here, this is the thermodynamics of the reaction. I didn't leave myself enough room. And everything in the middle here, we said, is the kinetics of the reaction, right? And so we sort of talked about this first kind of introduced this concept when we were talking about the thermodynamics of a reaction, right? So this corresponds to the kinetics. We then, when we introduce kinetics, kind of return back to this, but then we kind of like switched gears and we're looking at data, and we haven't really talked about this plot since, right? So how does that curve in the middle correspond to the kinetics of a reaction? So this height here, starting at your reactants and going up to the tippy top of that curve here, this is what's called the activation energy. Okay, so the height of that curve and the activation energy we're going to see is related to activation energy is related to K. So the larger the activation energy, the smaller that rate constant is, so the slower the reaction. All right. So anyways, how we kind of think about reactions is we think about them as if like I had this little marble here sitting at this energy level, and it wants to make it over this hump in order to get to the product side. Right. And so then the size of that hump, the amount of energy that has to be overcome, is going to be proportional to the rate of that reaction. Okay, so let's just take a look at two similar plots here. So let's say that this was one reaction coordinate diagram. And then in blue, I'm going to draw another one, which is going to start at the same energy as my reactants. Okay, but now it has a much smaller hump to get to the products. Okay, so these two reactions here would have the same thermodynamics, but my blue reaction is a fast reaction because that activation energy is small. So blue is fast. And my red reaction is slow because it has this much larger activation energy. So the red is slow, right? So that's how we talked about how the middle portion of this curve corresponds to the kinetics of the reaction. How is that? It's because the height of that barrier corresponds to the kinetics of the reaction, right? The energy that has to be overcome in order to get from products to reactants. Yeah, sorry if my audio is not great, or I mean, to be honest, the fact that we got internet right now is amazing because I live in the boonies here, and anytime there's rain, the internet is not so great. So sorry for that, but we're just gonna have to deal. All right, so the height of this barrier corresponds to the kinetics of the reaction. Again, the larger the amount of energy that has to be overcome, the slower the reaction. All right, so somebody came along and actually linked these two together. What is this dude's name? Arrhenius? How do you spell that? This is what's called. So this is a guy's name, Arrhenius. And he's got this equation that links the rate constant to a reaction to the activation energy. Okay. So this is our rate constant. Here is this new type of energy that we just learned about, again, corresponding to the height of that barrier. It's what's called the activation energy. T is the temperature, right? And R is that gas constant. And A is what we call the frequency factor. All right, and this corresponds to how many times you have these, you have your reactants combining and attempting to jump over that energy hump here. Okay, we'll talk a little bit more about this frequency factor here in a second. We're going to focus on this activation energy. Okay, so how can we measure the activation energy for a reaction? Again, we're just going to look at some data here. Okay, so this is another sort of method. Before we talked about analyzing initial rate data in order to get the order of a reaction as well as that rate constant K. So now if we do that a bunch of times and we get those rate constant Ks, okay, right? So we do that initial rate data to get the value of K, but then we're going to do the same process at many different temperatures, right? So in this set of data, what we're going to do is vary the temperature and measure K. All right, what we'll get is our change in temperature along with the change in K, right? So we're looking how that rate constant changes as we vary our temperature. And what this is going to allow us to do is to, well, so first of all, what we can do is if we take that rate equation, we had that K equals A e to the negative activation energy over RT. All right, now we have how this K is changing as we vary temperature, and everything else here is not changing, right? So that activation energy hasn't changed. A is going to remain constant, and R is, of course, a constant. So we can use this to measure our activation energy. Okay. And what they do is, truthfully, you could just take this plot and fit it with a curve nowadays. Back in the day, it was all about figuring out how to turn your data into a linear plot, because they were literally using like rulers and graph paper to measure slopes. Now we got fancy computers that do that crap for us, so we're not as concerned about it. All right, so what we need to be able to do is to take this Arrhenius equation here and analyze some data, some temperature versus rate constant data in order to determine the activation energy for a given reaction, as well as the frequency factor for a given reaction. Okay, and so just to remind us, this is this reaction here that we're talking about. Okay, so actually, let me reorganize this a little bit. At the top. All right. So again, we're going to learn how to analyze this data here in order to figure out the activation energy and the frequency factor for this reaction. Okay. Because if we look here, if we have the temperature, that's this term here in my equation. If I have K, that's this term here. We always have R because R is just that 8.314 that we're going to divide by 1,000 to put it into kilojoules. All right, so then the only two things that we're missing are the activation energy and the frequency factor. All right, so again, that's what we're going to be solving for here. Okay, so what we're going to do is, since we're trying to get to that activation energy, that's what we're going to focus on first, right? So activation energy. And we can even say we're going to solve for EA. All right, so we're trying to get to that activation energy. It's sitting up there in an exponent for E. So we're going to have to take the natural log to bring it down. So that's actually what we're going to do first, is take the natural log of both sides. This would give us that the natural log of the equilibrium constant. And in the magical world of logarithms, this multiplication between A and E becomes addition. So natural log of A. Natural log of E will bring down that exponent. So this will be negative EA over R times 1 over T. I'm going to leave the T out to the side since it's my variable and this whole thing is constant. All right. So I got the natural log of both sides. This equation here, both forms of this Arrhenius equation are on your constants page. So you don't have to have it memorized. You don't even have to know your log algebra. You just have to know when and how to use it. Okay, and so for the purposes of analyzing this data here to get this activation energy, what we're going to do is take the difference of these two data points here. I'm going to take the natural log of that second data point minus the natural log of that first data point, the K's for those data points. Then I'm going to put it in parentheses here, the natural log of A minus EA over R times 1 over, again, subtracting that second data point from the first data point. You can kind of make a note that that's what we're doing here. That's our strategy. Data point 1 minus data point 2. And then I'm going to subtract the first one, natural log of A minus EA over R, 1 over that first data point. Okay, you could actually switch them. Oh, which I did in this thing here. Gosh dang it. This is data point 2 minus data point 1. You could do it the other way as well. It really doesn't matter. You just got to make sure it's consistent on both sides of your equal sign. Right, so 2 minus 1, 2 minus 1. Okay. Now, before I even have go on here, I can notice that because A is just a constant, that frequency factor is going to cancel out. The natural log of A minus the natural log of A, that would be 0. So then this is going to equal, and then I'm going to pull out this constant here. I'll actually, pull it out with the negative sign. So this is negative EA over R equals 1 minus T2, or 1 over T2 minus 1 over T1. All right, so here I have rearranged this equation to make it easier to solve for that EA. This is the thing I'm trying to get to. So I'm going to rearrange this equation so that it's all by itself. I'm going to divide both sides by this 1 over T business. This term right here, this whole thing. Okay, and that will cancel it out from this side. That's why I divided by it. Okay, so this is what I'm left with at this point. If I want EA all by itself, I'm going to multiply both sides by that negative R. And that will cancel everything out on my right-hand side. And so I'm left with that activation energy. So then I can just plug in from my data table here. This over. Plugging everything in. This is negative 8.314 over 1,000 times. And I'm going to put these in parentheses in my calculator so my order of operations doesn't get messed up. the natural log of that second data point, 1.759, minus the natural log of that first data point, divided by 1 over the temperature from my second data point, minus 1 over the temperature from my first data point. Again, putting it in parentheses so that when I put it in my calculator, my order of operations doesn't get messed up. Where the hell are these calculations? Okay. All right, so punch that all into my calculator, and I would get that my activation energy is this 93.1 kilojoules. All right, and just remember why we did this. That activation energy corresponds to our reaction coordinate diagram. We talked about how the middle here corresponds to the kinetics of the reaction. And that activation energy is the size of that hump in my reaction coordinate diagram, right? The larger the hump, the slower the reaction. Remember, we also said that the endpoints, these points over here, they correspond to the thermodynamics of the reaction, right? So that's why I have this delta G here is just the difference between the energy of my reactants and my products. In this case, I can see that the reaction is spontaneous. It's a favorable reaction because the products are lower energy than the reactants, right? So then again, the kinetics was the middle. That's what we just figured out how to get is the height of that barrier. Okay. So now that I have all this, let's move this down now. I've figured out what my activation energy is. Okay, but in my analysis here, this natural log of A canceled out. So I didn't solve for A that way, but that's okay. Now that I have my activation energy, I can go back to my equation here. I can pick just one of these data points and plug everything in. And the only thing that I'll be missing is A, right? So I'm just going to pick that first data point. Doesn't matter which one. To the negative 93.1 divided by R. And that temperature, which for my first data point is 700. Again, I'm going to put that in parentheses so my order of operations doesn't get messed up. In order to get A all by itself, I'm going to divide both sides by this e to the mess up there. That will cancel it out over here. And so what I'm left with once I punch this all into my calculator will be the value of A. Okay, and when I punch that all into my calculator, I get a big number because e to the negative, all that stuff is a small number. And that is, oops, 2.11 times 10 to the 6. Okay. All right, so that's how I would take this temperature versus rate constant data and fill in my missing constants from my Arrhenius equation, the activation energy, and the frequency factor. All right, so let's talk a little bit more about this frequency factor. For A, we said it was 2.11 times 10 to the 6th for this particular reaction. Let's again take our reaction that we're talking about here. We talked about how the activation energy was the height of the barrier on our reaction coordinate diagram. Now, what can we learn about a reaction from the value of A? Okay, A is again called the frequency factor. A has two components to it, P and Z. Z is what's called the collision frequency. So that's how many collisions are occurring in a given period of time, right? And P is what's called the orientation factor. All right, so what are these two components here? So first of all, when we take a look at a chemical reaction, again, this is our reaction here. In order for this reaction to occur, there's got to be collisions between these reactant molecules, right? So they're in the gas phase, they're flying around, they're going to every once in a while smack into one another, all right? And a reaction will occur at that collision. But not all collisions are productive collisions or effective collisions. Not all collisions will lead to the product, the nitrogen monoxide and the chlorine gas. All right, and that's what's depicted here. If these two molecules collide in space, you know, this one's traveling this way, this one's traveling this way, and the oxygens on those two molecules hit, this would be an ineffective collision. It's not going to lead to a chemical reaction. Okay, if we aligned it such that the oxygen of one molecule hit the chlorine of another molecule, again, an ineffective collision. We're not going to have a reaction. We're only going to have a reaction if it's the chlorine end of both of these molecules that smack into one another. Okay, and that's not something that you would know based on this chemical reaction, based on this chemical equation or anything like that. The whole point here is that only a small fraction of collisions are effective. Right? Only a small fraction of collisions will lead to a chemical reaction. So that's what my two components of A are here. I have this collision frequency, how many times they're colliding with one another, and then this orientation factor is going to have a value between 0 and 1, and it's going to correspond to the fraction or the probability of a collision being effective, right? So you can kind of think of it as a percentage. What percent of these collisions are going to actually be effective collisions? So we can use this information here. I'm going to get rid of, make some more room for myself. We can use this information here to get some more information about our chemical reaction, because the collision frequency for gaseous reactions is 10 to the 9 collisions per second. So since I did all this work to solve for my frequency factor to solve for A, I know that's 2.11 times 10 to the 6th. That equals this orientation factor times my collision frequency. And since this is a gaseous reaction, that would be 10 to the 9 collisions per second. So then the algebra on this one's pretty straightforward. We can solve for P by dividing both sides by 10 to the 9. And what we're going to get is 0.00211. Yes. 0.00211. All right, so that's the fraction of collisions, or we can put it in a percent form by multiplying by 100. 0.21% of collisions are effective. All right, and to just sum up here, we were able to analyze our temperature versus rate constant data to get both the value of that activation energy, which corresponds to the size of the hump on our reaction coordinate diagram, as well as to figure out the frequency factor in the Arrhenius equation, which for gaseous reactions, we can go one step further because we know the collision frequency of gaseous reactions to actually determine the orientation factor of those reactions as well. Say just what percentage of collisions are effective collisions in a given reaction.